Alright, so in this video we're going to talk about limits involving infinity. And we're going to talk about limits as x approaches infinity primarily, but we'll talk about other things as well. Alright, think about the function, and here we have its graph. F of x equals 1 over x. So as x gets closer and closer and closer to 0, what do we know is going to happen? Well, we know that as x gets closer to 0, but the fractions are going to get larger and larger and larger in overall value because our number x is going to get tiny. We've talked about this already, where when we have 1 divided by some fraction, we're going to end up getting a number that's going to grow and grow and grow as x gets smaller and smaller and smaller and tinier and tinier and tinier. So there we actually see what happens to it as we get closer and closer to 0 from the left side. We take off to negative infinity because of the fact that the x is negative. And over here on the other side, we see that it's taking off to positive infinity because our x is positive over on that side. So what we're looking at here is the asymptotic behavior. We have a vertical asymptote at x equals 0, correct? Because that's going to make this thing undefined. That's how it's going to behave around those asymptotes. So we can say that the limit as x approaches infinity, well, we think about what's going to happen as x gets larger and larger and larger, and we see right here that this is going to get smaller and smaller and smaller as we get out there. Well, once again, in the same way we were talking about the fraction just a second ago, think about this value as x gets larger instead of smaller and tinier fractions. As we get 10 there, we got 1/10. As we have 100 here, we have 1/100th. And if we have 1,000,000 there, we have 1,000,000th. So what's going to happen as that x value gets larger and larger and larger is this value is going to get smaller and smaller and smaller itself. And it's going to approach 0. Now, the same thing's going to happen on the other side when we approach negative infinity. We can see that graphically right here, except for the fact that it's going to approach the value of 0 from negative numbers. So as the denominator is going to get larger, the actual value of that fraction is going to get smaller. And as the denominator is going to get smaller, the value of the fraction gets larger. That's the vertical asymptote aspect. So there's a horizontal asymptote for a function if the limit as x approaches infinity of that function equals some number b, in other words the limit exists, or if the limit as x approaches negative infinity of f of x approaches some number b. Now, you need to think about this for a second. This is one of those instances that's a special case. We talked about one-sided limits. Well, if we're approaching infinity, we can't get on the other side of infinity and come back. So that's not one of those instances where we're applying the two-sided rule for a limit. This, we're literally just looking at what's going to happen as x gets larger and larger and larger. Or larger and larger and larger in the negative direction. So don't get hung up on the fact that, oh, but to have a limit we had to approach from both sides. Not when we're going to infinity, because we can't get on the other side of infinity and come back. Contrary to what Buzz Lightyear might tell you. You can't go beyond infinity. Alright, so those ideas can come and take us to a situation like this. Well, notice here we're taking the limit as x goes to infinity. So x is getting larger and larger and larger, and this x is getting larger and larger and larger. What's going to happen to the 1? Well, the 1, as we've talked about in the past, becomes negligible. So insignificant as x gets larger and larger and larger. So we can think about this as x over the square root of x squared. And when we do that, we can take the square root of x squared, and we're going to get x over x, which is going to equal 1. So we have a horizontal asymptote at x equals 1. Alright, now this is one we've looked at before, but not in exactly the same way we're going to do it this time. Before, if you remember, we looked at the limit as x approaches 0 of sine x over x, and this time we're going to do it as x approaches infinity. So there's a couple of different ways you can look at this. We can look at the graph there, and what happens is x goes off to infinity in the positive direction. Well, we notice that we cross back and forth here, but what do we notice about our magnitude or an amplitude of our function as we get further and further out? Well, it gets smaller. Notice it starts big and it has an amplitude of 1 here at 0, but as we go on it gets smaller and smaller and smaller. Well, that's the case with the 1 over x. What we're literally really looking at this thing as is the limit as x approaches infinity, and we're expressing it not as sine x over x, but thinking about this as 1 over x times sine x. Now, if we talk about it in that way, what is 1 over x? Well, if you think back to when we talked about our trig functions, 1 over x is actually the amplitude. So what's going to happen as x gets larger and larger and larger to our amplitude right here is it's going to get smaller and smaller and smaller. Therefore, our periodic function, sine, is going to stop going up quite as far, and it's going to go smaller and smaller and smaller, and it's going to approach the value of 0, where it's not going to go on either side of that line, that x-axis very much at all. So that's what's happening. But let's actually look at this thing with the sandwich theorem again. So we know that sine x is going to be between -1 and +1. So for x approaching 0, or x greater than 0, we're going to have sine x over x is going to be greater than or equal to -1 over x and less than or equal to 1 over x. So when we take our limits as x approaches infinity for all three parts here, we got the limit as x approaches infinity of -1 over x, which is going to be what? What's going to happen is this number right here gets larger and larger and larger. That's going to go to 0. And over here on this side, what's going to happen is x gets larger and larger and larger. That's going to go to 0. So we end up with 0 here and 0 there. So what do we know that means about our limit as x approaches infinity of sine x over x? Well, it has to equal 0 as well. So use of the sandwich theorem on that thing actually works, and we can actually figure out what the limit as x approaches infinity is. So by the sandwich theorem, we know that the limit as x approaches infinity of sine x over x is equal to 0. Alright, so what can we do with a problem like this? We've got the limit as x approaches infinity of 5x plus sine x all over x. Well, if you've looked at your properties, on page 61 I think is the correct page, in your book, which we're working on, what do we know? We know that the limit as x approaches infinity of 5x plus sine x all over x can be rewritten as the limit as x approaches infinity of 5x over x plus sine x over x. And all I did there was I divided my x into both parts and split the fraction of it. We can do that. Now what we can do is we can take the limit and split that up, because the limit of a sum of two things is the same thing as the sum of the limits. What that means is that if I take the limit as x approaches infinity of this whole thing, it's going to be equal to the limit as x approaches infinity of 5x over x plus the limit as x approaches infinity of sine x over x. All right, so then we can actually do some algebra on this one and cancel out our x's, so we get the limit as x approaches infinity of 5 plus the limit as x approaches infinity of sine x over x. Now don't forget, don't make me mad and cancel these out. That doesn't work. You can't do that. Sine by itself has no value. It has to be the sine of something. So you can't cancel and bring that x out of the sine function. Now right here, what do we know is going to happen as x goes to infinity for the value of 5? Well, since there's no x attached to it, 5 is just going to be 5 no matter what x may be. So this limit right here equals 5. And we already figured out in the previous slide what this limit is. The limit as x approaches infinity of sine x over x is going to equal 0. So our answer is 5. Now, guys, here's the thing. You're going to have some problems that you're going to have to deal with where this and this may not be equal to just x. But here's the thing. As long as whatever is here and whatever is here matches up, you're still going to have a limit, as if we do this, of equal to 0. Same thing with the limit as x approaches 0. As long as that and that match, it's going to be a limit. The limit as x approaches 0 is going to be equal to 1. We'll look at some of those in class, so don't worry if that didn't make sense, but I'll show you that in some of the work in class. Alright, now, what about some infinite limits? Well, we've talked about limits as we go off to infinity, as x goes to infinity. But what if the denominator approaches 0? What we talked about at the very beginning happens as we're going to negative infinity or positive infinity, depending on whether or not that x is negative or positive. So I kind of jumped the gun a little bit on this part. But that's what we're doing. As the denominator approaches 0, the value of the fraction is going to get very large. If the denominator is positive, then we're going to go off to positive infinity because the fraction is positive. And if the denominator is negative, we're going to go off to negative infinity because the fraction is negative. So in this case, the limit as x approaches 0 from the positive side, giving us a positive x value of 1 over x, is going to go to positive infinity. And if we take the limit as x approaches 0 from the left side, or from the negative side of 1 over x, we're going to go to negative infinity. And we can see that in our graph here. Because we're plugging in values that are negative, 1 over a negative number is going to give us a negative number. So as that number gets smaller and smaller and smaller, it's going to take off to a negative infinity. Coming from the right side, our x values are positive. So as we go across here, we're going to add, or we're going to divide by positive numbers that are getting smaller and smaller and smaller. Our number, overall value, is going to get larger. It's going to be positive because the fraction is positive. So we do end up having a vertical asymptote at x equals 0, which we already knew. That we just looked at and we knew that that was going to be there. All right, now, in this case, with x squared being in the denominator, what's going to happen when x is positive or negative? Well, we're going to get the exact same positive number. Because any number that we take and we square, we're going to end up getting a positive number. So our fractions are going to be positive both times. So as x approaches 0 from the positive side of 1 over x squared, our limit's going to go to infinity. As we approach from the left side, it's still going to go to infinity because once we plug that negative value in here and square it, it's going to be positive and a positive fraction. Hold on. All right, this graph right here, I do want you to see this, because this is the graph that I call the volcano. And I'll give you a very ugly sketch of it, but as you get closer and closer, it's going to take off to infinity, and the same thing happens over here. So that, if you hear me talk about the graph that's the volcano, that's it. It's 1 over x squared. All right, end behavior models are very similar, and they're tightly attached to limits as you go off to infinity, because what we're doing when we're defining the end behavior model is we're asking what's the function going to do when x gets larger and larger and larger. That's why we call it an end behavior model. We're talking about getting out on the positive side where x is really, really large, and down here where x is really, really large but negative, and we're seeing what the function is going to behave like. A lot of times we can take and we can simplify this and get an easier function to deal with. So end behavior models model the behavior of a function as x approaches infinity or negative infinity. Now, this sounds a lot more complicated than it is, but all it is a test as to whether or not a model that you come up with, you've got to come up with a model on your own. This will be the test for whether it actually works. So a right end behavior model, as x gets larger and larger in the positive direction, the function g will be an end behavior model for the right side if and only if the limit as x approaches infinity of f of x, our function that we're dealing with, divided by g of x, the right end behavior model you've come up with, equals 1. If it doesn't equal 1, if it equals anything else, your end behavior model is not correct. So you've got to go back and come up with some other thing. Now, the function g is an end behavior model for the left end if, notice the only difference, f of x over g of x still, but as x approaches negative infinity, and it has to equal 1. Once again, if it equals anything other than 1, it doesn't work. You've got to go back and try something else. All right, so let's look at an example. All right, we're going to look at the function x plus e to the negative x. And we're going to come up with two end behavior models. We're not always going to have to come up with two, but this one has very different behaviors on either end. So there's not a single end behavior model that's going to work for both ends. So what we're going to do is we're going to come up with one for the right, and we're going to come up with one for the left. All right, as x approaches infinity, e to the negative x is going to approach 0. And the reason why is, remember, if we've got e to the negative x and we're putting in positive values here, let's say we've got e squared. Well, that's actually e to the negative 2. If x equals 2, we get e to the negative 2. Well, if x equals 4, we get e to the negative 4. And what does that mean? Well, remember the negative means you're going to flip it on the bottom. So we get 1 over e squared, 1 over e to the 4th. And then hopefully you can see there, as x gets larger, that fraction is going to get small really fast. Because remember, what's the graph of the e to the negative x look like? Well, it looks like this. So we know that that thing's going to go to 0. All right, so in that case, the x plus e to the negative x, the x value is actually going to dominate the value. That's not normal, usually. With the negative x is what's going to make that, e to the negative x is going to make that thing go to 0. Therefore, the x term is going to dominate. Therefore, g of x is equal to x becomes a good right-hand behavior model. And we can test that, not text. So if we test it, taking the limit as x approaches infinity of x plus e to the negative x over x, same thing we did just a second ago with the 5x plus sine x, we're going to split the thing up. So we end up with the limit as x approaches infinity of x over x plus the limit as x approaches infinity of e to the negative x over x. Now, this right here can actually be rewritten. We don't need to rewrite that. What's x over x? That's going to simplify down to 1. And what's the limit as x approaches infinity of just 1? Well, that part's going to be 1. Now, let's simplify this one. What I'm going to do is I'm going to drop that e to the bottom. So we end up with the limit as x approaches infinity of 1 over e to the x times x. Now, think about this. All I did was, because that x was negative up here, I can move it to the bottom. Remember, the sign of the exponent will change. So now I have 1 over e to the x times x. What's going to happen is x gets larger and larger and larger and larger and larger. Well, that denominator is going to get huge really fast. So what's this limit going to go to? 1 over really, really, really large numbers that are getting larger and larger and larger is going to go to 0. So that means that this part becomes 0, and 1 plus 0 equals 1. So we just confirmed that g of x equals x is a good end behavior model for our right side. Now we're going to do the exact same thing on the left. Alright, so as x approaches negative infinity, what's going to happen to x? Well, x is going to get larger and larger and larger, even though it's a negative number, but what's really going to control the value of this thing is e to the x, or e to the negative x, because, and here's the reason why. All right, so we've got the function. Let me make this, hopefully make a little more sense, because it's kind of throwing you off if you don't catch this. So we've got e to the negative x. But what happens as we go to negative infinity? Our x values are all going to be negative. So we actually are putting in here negative numbers. So we got negative 2, and then e to the negative 4, where this negative is this one, and then this negative is coming with the fact that the x values are negative. And what's a negative times a negative? Gives us a positive. So we end up with e squared and e to the 4th, and e to the 6th, and e to the 8th. And we're going to get numbers that are going to get larger and larger and larger. E, remember, is a thing that's going to grow really, really fast. And with e raised to a positive power, as we throw in negative values, then it's going to be the thing that's going to control the value. It's going to grow a lot faster than the x is. So therefore, e to the negative x is the dominant term of that, or the dominant part of that function at that point. So we're going to let it be our left-in behavior model. So e to the negative x becomes our left-in behavior model, and all we've got left to do is check it. So when we do that, you're going to get x over e to the negative x, and e to the negative x over e to the negative x. So hopefully you can kind of see what's going to happen here. Let's scroll down a little bit here, equals. And what happens? We end up with the limit, and I'm just going to write this as one limit instead of splitting it up like we did on the last one. We got x over e to the negative x. Plus e to the negative x over e to the negative x. And of course that's going to be 1. And what's happened to e to the negative x? Or e over e to the negative x? Well, what's going to happen here is we're putting in negative numbers, so as the x values are negative, 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 we put it in there, and they're going to make that thing grow really, really fast on the bottom. Because on the bottom we're going to have not e to the negative x, but e to the negative number x. I know that's kind of hard to see, but the same thing we had drawn up here just a second ago. We've got negative numbers going in here, so negative negatives gives us positive. So that means that this bottom is going to grow really fast, a lot faster than x is. Where x is going to go to infinity, you can think of e going to the negative infinity power, which means it's going to grow a lot faster. So this part right here is going to go to 0. And this part over here, e to the negative x over e to the negative x, of course, is 1. So we end up with 0 plus 1, which is going to give us 1 again. Therefore, our end behavior model for e to the negative x for our left end is going to work. Alright, so for this, our right-hand behavior model becomes x, y equals x, or g of x is x, and our left-hand behavior model is e to the negative x. Now, I'm going to show you a graph of these, and you can kind of see what happens here. What we're saying with the end behavior model is that this function is, as you let x get larger and larger and larger in that direction, this function is going to become more and more adhesive or similar to y equals x. And we can see that. As we get further over here, it almost becomes the same line. And on the other side over here, this is our actual function we were messing with, and there is our left-end behavior model. Here's our right-end behavior model. Like we just see it, it almost equals the same line over to our right and over to our left. It's going to take a little longer, but here is our e to the x, or e to the negative x power, and here is our actual function. It's going to get closer and closer and closer. It's just going to take a little longer and further away. But the values are going to be huge. Huge, huge, huge. And they're going to get huge really quick. Alright, now we've already talked about one of these when we talked about finding the horizontal asymptote. If you remember, a horizontal asymptote in a limit to infinity or negative infinity are pretty much the same thing. So our three rules that we talked about before are what we're going to use to solve a limit like this. So our right end behavior model, we can look at this and say, okay, well, what's going to control the value on top? Well, what's going to control the value on top is going to be that 2x to the fifth. What's going to control the value on the bottom? Well, it's going to be that 3x squared. So we talked about the fact that all that stuff was essentially irrelevant. It becomes negligible. So here are the dominant terms at the top and bottom. So what we end up doing is taking that and then simplifying it. So in this case, when we simplify it, we're going to get 2x cubed over 3. Now, before, when we were talking about vertical or horizontal asymptotes, this would tell us that a horizontal asymptote does not exist. Because what's going to happen is x gets larger and larger and larger for 2x cubed over 3. It's going to grow and be huge. Well, here's the thing. In the same way that that's going to be a simplified version of it, and it's going to tell us what the end behavior is going to be, or what the horizontal asymptote is going to be, it's also going to describe our end behavior. So this is the end behavior model for that thing on both sides. That's one of the benefits of dealing with a rational expression like this, is that it actually works for both approaching the left and approaching the right. So this right here is our end behavior model for both sides. Now when we go to find these limits, often you can just think through them. Let's take the limit as x approaches infinity of sine of 1 over x. Well, here's the thing. As x goes to infinity, what's going to happen to this blob in the middle, the 1 over x? Well, it's going to go to 0. So what we can then think about is instead of letting x go to infinity, we can redefine this thing right here and say, well, we're just going to let it equal x, and we're going to let x approach 0. And that's all we've done. We just redefined how this thing is. Since we know as x goes to infinity, this thing goes to 0, we can redefine our limit and say that we're going to take the limit as x approaches 0 of sine x. Now, what is sine x as you get closer and closer to 0? Well, what is the sine of 0? It's equal to 1. Oh, sorry, 0. I need to learn my trig, don't I? All right, that's it.